Having solved the Poisson's equation for a point charge particle in Cartesian coordinates in the previous lecture, in this lecture I am going to solve the same problem in cylindrical coordinates. The ideas are similar except that now the coordinate system is changed. The problem I am considering is a charge, of course point charge q at z equals z naught, s equals 0 in a cylinder of radius r. The axis of the cylinder is the z-axis and it is grounded. And we want to know V, S, Z inside the cylinder. So, of course, hollow cylinder. So, let me state this problem. The cylinder is of infinite length, its axis coincides with the z axis, and at z equals z0 is a charge q. The radius of the cylinder is r and it's of infinite extent in both directions. Then we want to understand what the field, what the potential is inside, and from that we can always calculate the field. Now this is symmetrical system. So there is no phi dependence. So symbolically, the potential V Sz is going to be of the form integration dk ak j0 ks e raised to minus k z minus z0 for z greater than z0, and this is going to be equal to integration dk vk j0 ks e raised to plus k z minus z0 for z less than z0. Now, since v s equals r, z is 0, that is the boundary condition. Instead of integral, I am going to have summation with k r being equal to x nth 0, where xn is the nth 0 of j0 x. And therefore, I am going to write now V S Z as equal to summation a n j0 xn s over r e raised to minus xn over r z minus z0 for z greater than z0, and this is going to be equal to summation bn j0 xn s over r e raised to plus xn over r z minus z0 z less than 0. Now, this is the solution. The equation I am solving is del square V is equal to minus q over epsilon 0 delta of z minus z0 and delta of S over S. That's the delta function in cylindrical coordinates. And I have written V as summation an j0 xn s over r e raised to minus xn over r z minus z0, z greater than z0, and as equal to summation over n bn j0 xn s over r e raised to plus xn over r z minus z0, z less than this. Continuity of V across z equals z0 for all s implies that an equals bn. So now we need to determine this a and bn. Then need to apply flux rule, which will say that V perpendicular dz over dz at z0 plus minus dz over dz at z0 minus is equal to minus q over epsilon 0 delta S over S. Substituting, since an and bn are the same, I'll get 2 summation an j0 xn s over r times xn over r is equal to q over epsilon 0 delta S over S. Now I'll multiply both sides by j0 xm s over r times S and integrate over S from 0 to r. And what I get is 2 summation n an xn over r integration 0 to r s j0 xn s over r j0 xm s over r ds is equal to q over epsilon 0 integration delta S j0 xm s over r ds. By using the orthogonality condition for Bessel functions, the left hand side becomes summation 2 summation n an xn over r square by 2 delta mn j1 xn whole square is equal to q over epsilon 0 j0 0. j0 0 is 1. So I get through am, then I had xm over r square by 2 j1 xm whole square equals q over epsilon 0. And that gives me a m equals, this 2 cancels, one of the r cancels, so am comes out to be q over epsilon 0 xm r j1 xm whole square. And therefore, the potential V as Z is going to be equal to summation AM and BM are the same, so I'm going to get Q over epsilon 0 xn r j1 xn whole square times j0 xn s over r times e raised to minus xn over r mod z minus z0. That's the answer. It can be written in a better form as q over epsilon naught r I can take out, summation n 1 over xn j1 xn whole square j0 xn s over r e raised to minus xn over r mod z minus z0. That's the answer. Let me now give you a question. What will be the potential if the charge was at S0 and Z0? Hint is that in this case there is no more a cylindrical symmetry, and therefore the potential V S Z will be of the form summation M n E A M n e raised to I m phi j m x n s over r e raised to minus, let me call it x m n over r mod z minus z0. And then you can expand and find the coefficients. Let me give you another related problem. Consider two grounded plates of infinite extent, and then I put a charge in between at a height z0 from the lower plate, which is at z equals 0, the upper plate is z equals d. And let this be right above the origin. Then find the potential everywhere. Find V and Z. Notice that a similar problem or the same problem was solved using reciprocity theorem earlier, but now we want to find an expression using Bessel functions and sine hyperbolic functions or the exponential functions, which is basically built up from the Laplace's equation solution. So let me conclude this lecture now. By stating that we have solved Poisson's equation for a point charge using cylindrical coordinates. Thank you.